everybody. Oh my gosh, so you either paid a whole lot of money to be here and you're hoping to get good information, or you're in here for free and just taking up time. Which one is it? No, I'm just kidding. Okay, so I always like to know who I'm talking to, because I just like to know who in here is an electrical engineer. All right, I love that. So we don't have to talk electricity basics with you. Other roles. Name something else. Who's sales? Who's mostly sales? No one. Great. Let's see. Who else would? Anybody work for a manufacturer? Manufacture products? You manufacture lighting products? No, just manufacturers. All right, great. So, John, thank you for that introduction. I'll tell you, every time I end up at WEC, it's always on a topic I know about, but I'm not a subject matter expert. I'm just going to say that right now. My background in design, I've done many projects where we've had to dim LEDs, we've had to dim fluorescent lighting, and so that's where this is coming from. But my topic today, and I thought it was interesting, was how does dimming affect LEDs? And I was like, okay, do we care about the LED itself? Do we care about the performance of the LED fixture? What do we care about? In an in-product type installation, you care about color, right? You don't want it to look crazy. You want to make sure it's as efficient as possible. You want to make sure it continues to work, right? Lifetime. So we're going to talk about those types of things as far as dimming is concerned. And there's a whole lot of other stuff sprinkled in as well. And because this is not my main area of expertise, feel free to throw out your other questions, related, unrelated, that kind of thing. And I'll do my best to tap dance. Okay? All right. So today's presentation, we wanted to talk about different dimming strategies, how they work. Because dimming LEDs is not the same as dimming incandescent, period. It's not the same as dimming fluorescent either. And so we're moving from one technology to another technology to another technology. The wonderful thing is the LEDs are wonderful for dimming because you're basically cutting power to them and having them turn on and off less frequently. So that leads to really great outcomes. It's just like LEDs like the coal. So we're going to learn about how dimming affects LEDs, the challenges associated with dimming, and flicker comes into this as well, even though we have to remember lights flicker. You don't need dimming for that. Dimming is just another piece that just makes everything worse, right? And then we're going to talk a little bit about some strategies for solving dimming problems, which most of them I hate because it almost always ends up with adding more load to the circuit, which we're trying to solve, save energy. And we want to add an incandescent to the circuit so a dimmer will work properly. So, all right. So all these electrical engineers in here, I always like to start with the sine wave. Ha ha. So everybody knows what comes out of your outlet is light, is power oscillating. And this is one period, and this happens how many times a second? 60. So look at where the power hits zero twice during that one cycle. So for a second, that happens 120 times, right? Okay? So what happens with dimming and how we started dimming, and he talked about forward phase dimming, we're basically chopping the wave chopping. And forward phase means you don't turn it on first. There's a delay, and then it crosses, and then you turn it back off as a delay. Well, that one's not a great way of dimming LEDs. So I almost would like to say, if you see anything that says forward phase and it says LED, stop right then, because that's not how you typically will dim an LED. And most of the reason has to do with the fact that you have power conversion in your driver, and so the driver is the thing that You don't want the driver having to play with this wave. The solid state device that isn't a dimmer that does forward phase dimming does not work well with electronics. Become electronic low voltage, but a driver would have the same type of circuitry. It's not that circuitry that's needed. It will be the circuitry that you would need for reverse phase. The other piece of this is forward phase dimming throws a whole lot of inrush current back into the system. That's why we end up with all this derating. I'm not sure if anybody realizes, but you can't just use a dimmer that says it's 800 watts. It's good for 800 watts, and you can't throw 800 watts worth of LED load on it. It's not looked at the same way. So let's see here. So reverse phase takes care of this issue, because if you look at where, and let's see if I got my pointer. Look at where it hits 0. So it's off. This is the part that caused the inrush. But here, we're actually solving the problem with reverse phase. And we have wonderful Lutron people here who can talk to you all about the different kinds of reverse phase dimmers and dimming protocols. Okay, I'm going to keep going. All right, John touched on this somewhat, but I always like to talk about dimming in terms of what does dimmed mean to you. If somebody said, I want this room right now dimmed 50%, what does that mean? 50% of what, right? You want 50% less power use? Because that's one thing. You can say, this room right now is taking 1,000 watts of lighting power. Let's put it to 500 watts. Do you think it'd be 50% of the light output? No, not really. Are we talking about measured light? Right now you maybe have, 30-foot candles at your tabletop, and we want it to 15. So that's a percentage of dimming. But you have to be really careful when you're talking about how you want something dimmed as far as the percentage. So, and then not only that, so we're talking about foot candle levels, which is the illuminance, versus the actual light that comes out of fixture, which is going to be how many lumens come out. So lumens don't equate to the light level you will find on your tabletop. Then how much light you think it is. Because people say 1%, and people assume that 1% dimming, does that mean out of all the light that was coming out of it, now it's only 1% of that light? Maybe, maybe not. So you have to be really careful when you start talking about what does 1%, 10% dimmed mean to you. And then also, because your eye does wonderful things. The brain is so amazing that you can work under the same light level and somebody adjust it, just a little bit, and it'll throw you off because you just have been so used to what you've been sitting under. Also, dimmable, it could mean, well, I have a dial, or maybe it's just a digital device and it has 50 on it. That doesn't mean much of anything other than the device says 50% of where it was. Just like when you have your it's not a rheostat, but thank you. Huh? Yeah, but the dimmer on the wall, the rotary dimmer, right? The rotary dimmer, when you turn it, you expect certain things to happen, right? You could turn it all the way and the lights feel like they're almost the same. So the control signal, I dimmed it 50, meaning I turned it halfway. Does that mean you dimmed 50%? No. So you have to be really careful. And so, John, you talked about this somewhat, and I wanted to make sure I pointed it out. But so the light level that is measured versus what your eye perceives is really interesting. So if you look at the red right here, it says that we have 50% less light. But your eye detects it as, it's only been dimmed about 70%. So that's why 50% dimming doesn't necessarily mean it's needed. Like for this room, all these lights are on for a presentation, which is kind of interesting. But in most presentation rooms, you would expect a lower light level, if I said I'm doing it to 50%, meaning I measure it at 50%, you still may feel like it's too bright in this room. And so the same with the blue line, which is at about 25%, that's where it feels like the light's been dimmed only 50% as far as how we perceive it through our eyes. Okay. All right, so Mr. Lutron down here will probably talk about dimming curves, but I'll play with this a little bit, and I'm not sure how well you guys can see this, but so right now we have 3 curves shown up here. So dimming curves can be linear, meaning when you turn it, it reacts exactly how you think. So this, let's see, is it the first line? Is the second line? Look at the first graph, the green line. So linear output would be this, straight 1-for-1 performance. What we're really trying to do is we want to combine a linear input with a logarithmic input. So the light that you see, it adjusts the way you expect it to. So look at the yellow line in every graph. So the first one combines linear with logarithmic. And so you'll see that the perception of light, it doesn't just, it ramps up like you would expect it, pretty close to what we expect linearly. But look at this, well, actually, no, excuse me, guys. The second one actually does that when you combine, give me 1 second. The first one is the more ideal, excuse me. So look at the second, look at the yellow line, and you'll see where the light level ramps up pretty quickly. You see that? And it ramps up pretty quickly where we're only here, but the lights come up so fast. And then the second one, which is it's more logarithmic input, even though you've got the control doing what it's supposed to do, the light doesn't ramp up until the very end. So this is important when you have control devices. The people are turning and punching buttons and expect things to happen. The same as like when you want to dim something, you turn it all the way to its lowest setting, but then the light's still on and you expect it to be close to 0. So what I'm really saying is there are different ways of dimming, and a logarithmic and linear type dimming protocol are together are typically the best types as far as a user interaction with a dimmer. All right, I always like to include pretty pictures because most of the slides are a lot of words. But so this is an LED application where you would expect in a high-end restaurant, this has to be dimmed, right? It has to be dimmed. And so how do we get that accomplished? So let's talk about LEDs. 2 years ago, I did a presentation on LED drivers, the basics of LED drivers. And people don't realize how important the driver is to the success of an LED installation, but it's ultra, ultra important, because what's happening with dimming is that you have a dimmer that is interfacing with the electronics of the driver to control the LEDs. All right, so John, we're going to be talking a little bit about what you've already talked about, but these are different modulation protocols. So pulse width modulation dimming, which actually is it's pretty common. It's actually a pretty common protocol. This is when you have constant LED current and you vary the duty cycle, this on and off time. So you can see where in the graph between 100% and 0, it's turning on and off. So this is good dimming regulation when you want to do deep dimming. It gives little color shift, but Pulse width dimming is a big flicker issue. That's where we get really concerned that flicker may be a real issue. And the other part too is that there's a potential for noise, and we'll talk about noise a little bit. So constant current reduction dimming is when you're varying the current to the LED, but the LED actually always stays on. See, the pulse width modulation is turning on and off. The CCR piece, it's always on, except it's on at a lower level. There's no flicker associated with this, and little to no noise generation. You end up with potentially higher LED efficacy at lower dimming levels, but you can have poor dimming regulation when you're trying to do very, very deep dimming. And then there's a potential for color shift, and we'll talk about why this is. So the hybrid of that, and basically if you look at the first two graphs, basically you're adding them together to get this hybrid where you are varying the LED current and you're also varying the duty cycle, meaning, but the LED is never off. And this gives you little to no flicker. It takes care of your noise issue and keeps the efficacy for the LED up, and then and is really good for deep dimming and really no color shift. So as far as the effect of dimming on LEDs, we'll talk about efficacy because, so remember, what is efficacy? It's a ratio, a calculation between the light that's being emitted and how much power it takes to make that light, right? The LEDs are interesting, right? So what, anybody see any literature that says 100 lumens per watt? What's your baseline efficacy? Anybody? Throw out something. I've seen 200 lumens per watt, 50 lumens per watt. Anybody know how efficient an incandescent lamp is? Huh? It's not 45, which is now the federal minimum for general service lamps. So LED luminaires right now, 150 lumens per watt is, I won't say typical. That's some of the ranges for the Design Lights Consortium. But when you get to the LED itself, you can have an LED that's 180 lumens per watt easy. It's really the optics that determine how much light you get out of an actual luminaire. So we're talking about how much light we get out for the same power, basically. In this case, if the temperature varies and the current is constant, the efficiency will decrease if you have higher temperature. Remember, LEDs light the coal? They put them in all the freezers and stuff. You go into Sam's now, you walk down the aisles, and they're all pixelated, but it's light. And then the nice thing is they're controllable, so you can put them on an aux sensor. Well, LEDs like the coal. They don't like the heat so much. Heat sinking has been a huge issue with LEDs. So if you look at the chart, you can see the junction temperature for the LED at minus 25 degrees C. We're doing great. We're at 80 lumens per watt. And as we go up to 25 degrees C, which is kind of typical, it goes up somewhat. But you see what happens when you keep increasing the temperature at 120, and if this graph extended more, you'd see that it could plummet. So temperature increases for LEDs really affect efficacy. But there's an interesting thing that happens because LEDs, you typically have a blue LED with a phosphor yellow pump over top of it. That's how most white LED lighting is made. Depending on how the temperature of the junction of the LED affects the whole package, you can actually get a spectral shift, which basically results in more light, luminous flux coming out. It doesn't last very long, and there's a sweet spot for it, but that is an actual occurrence that can happen. So efficacy is affected as far as temperature. We know higher temperature lower efficacy. So what happens in dimming, we can, depending on the type of dimming you're doing, if you're adjusting, if the current stays constant, just like we talked about with the hybrid before, or the CCR piece, you can see some decreases in efficacy. Now, if you are changing your current and keeping the temperature constant, remember, LEDs respond to the current that you give it. And so, remember 350 milliamps is the typical what you expect to drive an LED at, but then people start driving them at 700 milliamps, and you see some driven at 1.5 amps, and so on and so on. It just depends on how a manufacturer actually makes their product. So it's widely accepted that the light output depends on the drive current. If the same LED you put 350 milliamps to will be a lower brightness than if you put 700 milliamps to, right? And I'm not saying it's linear, but so look at the efficacy on the y-axis, and so we have an LED, CFL, and an incandescent bulb. And as we, the more we dim, the lower it goes. So depending on the LED die construction, the efficacy typically reaches a maximum at a particular current level. And then below that, efficacy begins to decrease. So there's always this sweet spot there. But as far as dimming is concerned, efficacy is something that is affected. The driver efficiency will also have an impact. And we don't talk about driver efficiency often because we like to talk about how efficient LEDs are. But if you have a driver that's not terribly efficient, that will determine how efficient your luminary is, the efficacy of what comes out of the whole package, not just the LED itself. All right, so lifetime is affected. The LED, how long is it going to last? And I'll tell you this, we're not going to talk about reliability. There are not a lot of good studies. Well, there's studies, but now they haven't been translated into great specifications as far as reliability is concerned. You know, we talk about the bathtub curve, what's going to fall in and out as far as manufacturing tolerances, but when we talk about 25,000 hours, we've heard that, right? 50,000 hours, 100,000 hours. Anybody seen anything that says something last time? The guy in the thing yesterday, in the opening session, I heard him say 100,000 hours, and I just cringed because, the projections. Nobody's run all this stuff for 100,000 hours. But that's really just talking about the life of the LED itself. We're not talking about the driver, which is where the electronics are, which is where you're going to see more of the failure modes. The life is based on lumen maintenance, and that means how much time you expect to get a certain level of light out without a certain level of degradation. So L70, you'll hear that term thrown around a lot. So anyway, dimming normally increases the usable life of LEDs because guess what? It's on less. You're doing this cycling on and off. And so you typically have a better life from dimming. And the nice thing is, most LED systems are dimmable if you put the right system together. So you can literally have a system in place where it's been dimmed the whole life of the installation. You can actually set your max at a dim level to get more life out of those devices. It also decreases the thermal stress. Dimming typically is at a lower drive current and of course is off for longer periods of time. But small changes in an LED temperature can have a dramatic effect on life. So if an LED junction temperature is supposed to be at 90 C and you're running at 150, you can expect that LED to shift and fail. That's just what we've seen over time. But reducing the junction temperature from like 74 C to 63 C, it increases the rated life of that device from 18,000 hours to 30,000 hours. So that is a way to be able to get, these devices to where the LEDs last that long. But like I said, the real issue for most reliability has to do with the electronics in the circuit. Now the LEDs can depend on how they're made, the junction, the packages around the LEDs can also fail as well.
It's Fahrenheit, not Celsius, right? 74.
Maybe.
Yeah, 74
Yeah.
Celsius. 100
Yeah, because that's 25 to like 15. Yeah. Okay. Thank you. I thought I had the table in there, and that would have helped me, but I did not put it in there. All right. So the color of LEDs get affected by dimming as well. We all like to talk about color shift and the rainbows on the wall because it's kind of cute to talk about. But color shift early on in LEDs, and then I'm not talking about dimming. I'm just talking about in general use. You could put something up and watch it turn purple. We saw a lot of that with early city installations and parking garages and that kind of thing because of heat management. So it's really a temperature issue. So you can see, so when the temperature is allowed to vary, color can be an issue. But now the real interesting part for me was that depending on the color of the LED itself, now we are typically talking about white light, right? But so white light LEDs, which are still really blue LEDs, tend to be a little bit more stable. The phosphor over top of it keeps it a little more stable. But if you're looking at, very static color LED, red, blue actually shifts a whole lot more based on temperature than white LEDs. But just knowing that when you dim, you've got a lot, when I say it's a lot going on in that circuit. You've got a driver that is being basically talked to by some type of controller telling it what to do in order to dim it. That you can affect color because if you're not managing the temperature properly with whatever protocol you're using, then you have that potential for variation. All right, so challenges with dimming LED, flicker. All right, flicker. Ugh. I'll tell you this, flicker is huge right now, mostly because there have been a couple of standards that have come out. The IEEE came out with something back in 2015, which was supposed to be more like biological effects, and they came out with a pretty stringent curve as far as how much flicker something can exude. And this is not just in dimming. It's more critical in dimming, but it's actually typical in normal installation. Well, the fun part about what the IEEE came out with, guess what? The incandescent bulb would not meet this standard. And so the standard was based on risk. It's based on exposure. It was based on seizures, migraines, that kind of thing. And we know that magnetic fluorescent had those issues. There's a lot of historical information, but when it comes time to actually finding real data to make a recommendation, people tend to side on the more stringent, more conservative side. And so this is what the IEEE did. NEMA just published a standard, NEMA 77, this spring, which is the standard for temporal lighting artifacts. It's a test method, and it has a guide or more acceptance criteria for dimming. They talk about, let's see, so PST, which is short-term flicker indication, and then the SVM is stroboscopic visual measurement, these limits, in order to say, well, what's acceptable? You have to remember flicker is dependent on the waveform, how you decided to dim it. It's dependent on the duty cycle. It depends on how often the product is being turned on and off. So multiple things that go into determining whether a flicker level is okay. You can say 30% flicker is okay, but only at certain frequencies. So that's why I consider it a convoluted curve. You can see that the green piece, the green piece is supposed to be where it's an acceptable level. The yellow band is the low risk, and then everything above it is supposed to be, it doesn't say high risk, but if you don't say it's not low risk, what do you assume, right? Risk. Other organizations such as the LRC have come out with recommendations. I think this recommendation has been out for at least 5 years, back during my Energy Star days, which talks about what is acceptable. There have not been enough real studies to see what is an acceptable range of flicker for particular applications, because we all know that the lights outside flicker. Like, if nobody's complaining about the street lights flickering, because you're not really out there. It's not causing those kinds of issues, versus if you're sitting under a light that's flickering, even if it's not visual flickering, it's just stroboscopic, then it may cause an issue. So these are some of the somewhat guidelines. I'm gonna tell you, I wouldn't use these except to just say, well, I think it's about this. Because there's just so much data out there right now. Right now it's time for many organizations to come together and decide, how flicker will be addressed. But it is a major challenge when you're dimming. Also, dimming, you end up with audible noise. There are multiple reasons why you get noise on the circuit. You can do improper loading of a dimmer. I talked about that, the 800 watt example. And then John spoke about this, and Mr. Lutron as well, that compatibility is a huge issue. I remember when I first started doing line design, it was like, mock it up, mock it up, mock it up. And we're not talking about dimming. This was just mock it up because we want to see what a light looks like. We want to see, before I put this on my spec and it's going to cost my owner, $100,000, I want to make sure that it's going to look like what I want it to look like. The same thing happens with compatibility, but the nice thing is that dimmer manufacturers, controls manufacturers, that they're all over this. This is important Acuity Brands, we make a lot of controls as well. We're all over this. This is important to us. No one wants to say our control doesn't work with some device. So it's out there, but it is something you'll have to make sure you're paying close attention to. It's a question that you end up asking. I will mention that there will be an announcement in the next month of a program that NEMA has put together that basically takes all the Energy Star lamps and kind of matches them up, kind of like the Garanimals. Remember the Garanimals? It matches you up with a proper dimmer. And so there's a program that will be launched. So keep your eyes peeled for that. But that was in response to the fact that dimming and dimming controls, the compatibility is such an issue that they put out standards SSL 7A and 7B to make sure it's not an issue. Okay, and then, all right, so the last couple of things I always like to just play with these. So solving dimming problems is sometimes setting the low end trim on the dimmer. That's really where you don't want to turn it all. If you want turn it all the way to the low setting and it's still at 50%, you might need to do something. Then you can try a different LED lamp, a different dimmer, like add more load, which is always bad, but check the wiring, check your dimming type, compatibility, and then of course inrush, as John said. And then this is key. If you're gonna source something, check it out and use quality suppliers. When I say quality supplier, I mean go talk to somebody who used that person already. If I can't stress anything, like he said, we have a presenter that his company is out of business. Okay, you want to use suppliers that you can trust and who will make it right if it's not right, that kind of thing. So With that, if there are time for questions, no times for questions.